With fossil fuels being mainly responsible for greenhouse gases and global warming, the search for a new, clean and efficient method of satisfying the world's energy needs has become one of the primary scientific and technological goals. While renewable energies like wind, water, and solar can complement conventional energy production methods such as burning fossil fuels, nuclear fission, a new major energy source will be needed if mankind's energy consumption continues to grow at its current exponential rate. The most likely candidate for this role seems to be nuclear fusion. Nuclear fusion is nature's foremost method of producing large amounts of energy. It fuels the sun and other stars, bestowing Earth with light and comforting warmth. Harnessing the sun's power would give us a clean, safe, and nearly inexhaustible energy source. While numerous scientific institutes and centers around the world are working hard on achieving nuclear fusion, some serious technological obstacles remain. Joint European experiments like JET in Great Britain have proven the working principle of nuclear fusion reactors, and ITER, the world's largest fusion experiment, is currently being constructed in the south of France. Nevertheless, the path to commercial energy production by means of this scientific principle is still a long and rocky one. At the University of Technology in Vienna, Austria, the Group for Atomic and Plasma Physics conducts state-of-the-art research concentrating on the removal of one of those rocks from said path. In a fusion reactor, the walls will have to withstand tremendous heat loads and repeated impacts of energetic particles from the fusion plasma. A plasma is basically a very hot gas containing a mixture of ions and free electrons.
More than 99% of the visible universe, our sun and all the stars, are made out of plasma. Solar winds and northern lights are also plasma phenomena. On Earth, plasmas usually have to be produced artificially, like in neon signs, plasma TV screens or plasma cutting devices. And when a hot plasma comes into contact with a solid surface, a whole slew of new phenomena takes place.
And these phenomena must be studied and understood so that scientists and technicians working on fusion experiments can build reactors able to take the steady bombardment with energetic ions and electrons. But the interaction of ions and surfaces is not only of crucial importance for future fusion machines, it also opens numerous doors to technological applications, advancing, for example, the production of computer chips, medical research, and biotechnology. But before those ion-surface interactions can be studied, the necessary ions have to be produced. This is done in an electron-cyclotron resonance ion source, lovingly nicknamed SOFI. Inside the source, conditions similar to those in the sun's interior are created to ignite the plasma. Mind you, that's several million degrees centigrade.
Once the plasma is burning inside SOFI, the ions can be extracted by means of electrostatic fields. After leaving the plasma chamber, they are guided by magnets into one of our 3 beamlines, where they impinge various surfaces and where several experiments are conducted.
One of these experiments is designed specifically to investigate the damage a reactor wall takes when bombarded by energetic ions. In the so-called quartz crystal microbalance, QCM, a cylindrical quartz crystal is coated with the material in question and then bombarded with ions. The crystal is then forced to oscillate by an intricate electronic arrangement.
The change of the oscillation frequency of the crystal is a direct indication of how much mass has been removed by the incident ion. The more mass has been spotted away from the surface, the faster the crystal oscillates after bombardment.
But not only mass removal can be measured using the microbalance. Since mass increase also changes the eigenfrequency of the crystal, the QCM can also be used to measure ion implantation and the adhesion of molecular ions to surfaces with high accuracy.
With our self-built quartz crystal microbalance, we are able to detect mass changes of as small as 1/1000th of a milligram. That accounts to the removal of single atomic monolayers,
making the QCM one of the most accurate scales on the planet. Another important group of experiments conducted by Vienna's Atomic and Plasma Physics Group concerns the structural manipulation of surfaces with ion beams. To observe the changes a surface undergoes when irradiated with an ion beam, the scientists study the materials under an atomic force microscope, allowing them to look at changes on an atomic scale.
After looking at various surfaces bombarded with slow, highly charged ions, we were surprised to find that the impacting projectiles have not produced craters as you might expect, but on the contrary, hillocks, like little mountains on the surface.
It seems that the potential energy, which was stored in the projectiles when they were produced in the ion source and transferred to the surface on impact, has resulted in a phase change within the solid. The ability of slow, highly charged ions to trigger localized, nanoscale phase transitions in materials can be utilized in various technological applications.
We have found a new method for melting materials on a nanoscale. This might be interesting for various technical applications, since by highly charged ion impact, not only a phase transition from solid to liquid, but also a transition from crystalline to amorphous, or even from non-magnetic to magnetic is thinkable. This kind of material modifications might be of high importance for semiconductor and nanotechnological applications.
Other experiments conducted by the group include studies of electron emission from fusion-relevant materials, the development of diagnostic methods for fusion plasmas within reactor environments, and guiding ions through nanocapillaries. Research in how ions of various kinetic energies and charged states interact with matter can not only help make nuclear fusion feasible for commercial energy production and advance various technological fields, it can also help us comprehend various natural phenomena involving plasmas, and therefore deepen our understanding of the world around us.